Preview.
So a team from the Department of Chemistry here at the University of Bath have just received a major EPSRC programme grant, a multi-million-pound grant, to investigate the properties of a new class of what we call functional materials. That is, materials with some physical property that might be of value to us. We are using a type of material called a metastable state material in order to induce not only a desired function for our materials, but being able to switch that function on and off. Now, the idea of a metastable state material might be quite difficult to grasp, but we can relate it to everyday objects. And I'm going to give you two examples, one of which you would not consider to have some sort of alternative physical state, and one which you would recognise as having an alternative physical state. So the material which does not have a recognisable alternative physical state might be something like this table. So I'm hitting this table, it's a solid object, you don't really consider that that table is going to have an alternative physical state that might, suddenly allow my hand to go through or something like that. But let's take another everyday analogy of something which does clearly have two different states. Let's take a balloon.
A balloon in its uninflated state is malleable and it's flexible, and it has very little tensile strength. But once you inflate that balloon, if you like, put energy into the process, then you have an entirely different properties, much more rigid surface. Obviously, if you pop it, you lose the energy, you return to what we would say equilibrium state.
And so the physical properties are dramatically different between the inflated balloon and the initially deflated balloon. And it's that analogy, it's the chemical and materials analogy to that we are going to explore during this programme on metastable state materials.
So what we would like to do, and what we plan to do in this programme, is to develop whole classes of materials that we can put into a metastable state and control. For example, one of the properties we want to change is that of colour. Now this, on the face of it, might be a very simple property to change, but wouldn't it be fantastic if you could change the colour of your wallpaper, change the colour of your car at will?
Now, most of us drive a car. I drive a car, and it so happens actually that my car is a fairly dull light blue, and it's not very exciting. And just occasionally I go out to my car in the morning and I think, well, actually it's such a sunny day. I would really like that car to be a different colour today. So wouldn't it be fantastic if I come out on a sunny summer's morning to my car, which is coated with some wonderful optically responsive paint, where I can take out my car keys with a little remote control attached, select a button on my remote control, send a signal to the coating on the car, which makes it change colour to, say, a bright yellow for a sunny day.
And by simple electronics, you would be able to switch the colour of your car at will. So on a Monday you might want a blue car, on a Tuesday you might want a red car.
Wouldn't that be fantastic vision? Well, actually, the sort of science that we are developing in generating these metastable state materials, the sort of control that we want to develop over the optical properties of materials, might well make something like that become a reality.
So we have a very expert team at the University of Bath who will make new materials, measure the properties of new materials, calculate how the properties may change. Then, by an iterative process involving experiment, measurement and calculation, we will optimize those properties. So that's the fundamental science, and I think we're the only group in the world taking this approach with these metastable systems. But I think one of the key features is that within our 5-year program, we certainly plan to try and get some of these new materials into devices with real applications over the 5-year period.
And this is one reason why we've managed to secure this major tranche of funding from the EPSRC.
But this is only the beginning. I think what's particularly exciting about this project is that we can see the vision for the 5, 10, 25, 50-year future. And this is just the start. What we do today, we hope will influence how materials science changes over the next 50 years.
That's fantastic.
Preview.
The really exciting thing is the speed of the change.
shockwavesound.com